So Assalamualaikum. Hari ini kami from Dubai. Today we going to present our product on SWE-M system, which is my pregnancy system. So first, let's go through the problem identification. So our system comes from the inefficient vehicles monitoring in Malaysia that has led to overloading of commercial vehicles, which leads to restoration in road deterioration and safety risk. Current solution to this is just roadblock and static weight brake system. So the cause of this problem is the ineffective and discontinuous monitoring system, and possibly depends on manual check, which is the roadblocks and static weight system, and no real-time detection regarding this. And for our target user is GPJ, which will benefit the most by using this system. Next, for total solution and benchmarking, so we come with the idea of SWE-M system that measure vehicle weight and axle count in real time without the needing to stop the traffic. And there is also automatic vehicle identification using camera-based license plate detection. And this is basically the benchmarking on the current solution out there with our system. So our system doesn't require the vehicle to stop, no traffic disruption, and the monitoring is done in real time. Also, vehicle identification is automated. No need to you look at the vehicle, plate number, etc. No, it's automated, camera-based, and also the monitoring coverage is continuous and automated. So compliance consideration for our system will be the condition vehicle verification due to the passport. And those who involved with road safety and public infrastructure protection. Next, for system architecture, this is basically the same. Okay, this is gold dot, and here the camera to detect the plate numbers, and also to detect the presence of the car of the vehicle. Also, the bollard is just for the housing for the whole system. This is basically the content that we put in the house, and this is beam which will attach the string gauge on that. Okay, next for design specification table, which is based on the user need and our engineering target. So first, weight monitoring system. The weight monitoring, we come with the system that able to withstand up to 12 km load without detonation. And for vehicle data collection, with at least 90% of capture rate and also recognition accuracy, where it means that we can detect the plate numbers accurately. And also overall the system just provide smooth traffic flow, no congestion. Next, this is the design idea, basically how does the system works in the real life. So this is the bollard, then this is the vehicle. So basically the vehicle to come here, how the system works is the camera will detect the presence of the vehicle, and then we'll start the move of the system. And then when the vehicle starts always waving brake or just leave, it will detect the weight of the vehicle, and then it also will detect the axle count of the vehicle, and then the system will stop moving once either there are a new vehicle, or the system no longer detect any vehicle within 2 seconds. So this is basically the design analysis. calculation we came out with, so that we get to achieve our engineering target to withstand up to 12 km without the machine. This calculation, and this one is a calculation for the camera system, where we want the camera to detect the plate numbers accurately in the range of 5 meters. So basically, we find the angle of the camera, the specification we want to use, etc. So this is the prototyping process. This is the graphical. For engineering target, we have like 5 different stack for the weight detection, access detection, camera data detection, overweight classification, and also system group. And for verification process, how we that process, this is the result that we get. This is rate of success that we put. Yes, there will be improvement. But then, why does it goes up to 100? It's because that okay, for instance, for the measure vehicle weight, this system should be used when the vehicle are moving. But then we only get to try with the static vehicle. This is very sensitive. Okay, so for social, environmental, and economic impact assessment, there are okay, for in terms of public safety aspect, by implementing the system, so it will improve the highway safety, thus reducing the public trust, and also with the automated and continuous system, the traffic efficiency will improve, no need to roadblock, etc. Also, the environment will contribute to the environment as well, since we are reducing the vehicle speeding because of the roadblock, and lower load lower the atmosphere cost through the reduced manpower dependency, because the systems are automated. For the stakeholders, these are those who are affected in a good way once the systems are implemented. And these are the regulatory and economic considerations. We divide it into like 2 categories: regulatory and economic feasibility. So basically, when this is when we implement the system, they indirectly benefits from it. So that's it.
Your output is just from, I mean, the weight that is appeared is just shown on the screen. You don't have anything like something that will appear, you know.
Oh, like LCD.
Yeah.
No, because we plan to do it like cloud based. Yes.
How does the beam will measure the weight of the vehicle? Because here, yeah, it's okay, no, that's fine. Let's say it works and gives you the weight like you showed. But this one, I mean, the vehicle is like this. You have two axles. So which weight you're going to get from the vehicle? Because when you get the first wheel, you get the first axle weight, right? With the engine, if the engine is in front. Then you go front, then you lost that one, you know. Because it's instant. You have the weight actually localized. The current one that they use, you have the whole truck like this, and they have sheet like this or whatever, the balance or the weight, to weigh the whole thing. But now you weigh it like this.
You will go through. So every time it's
Yeah, but it's not the same weight.
Yeah, we accumulate.
How?
At least
This one here, this is my balance. But this one, the weight that I have of that. After that, probably I don't know difference. I don't think it will be the same weight of the whole vehicle.
So basically, what we are doing is actually calculate the total axle weight. So for every vehicle that pass through the beam, it like a truck has two axles. So the first axle we get the first calculation, first weight, and then we store it first, and then the second axle when pass through the beam, we get the next
Second weight.
Any proof this approach is correct?
because we calculated the axle, how we did it is actually we add up all the axles that
Any proof? Okay, let's say the lorry is something that is measurable. Let's say you have something 50 kilos or whatsoever, right? You put it for your thing. You put it at the front first, and then you put it at the back. You accumulate, you plus it, right? So is it the same total as 50? You get 50. Any proof? Any proof?
We haven't done it yet here because we have some.
I think it's just a simple test, right?
Yeah. But I don't think it will work. Because usually, I don't know if there is there a mechanism using this to weigh vehicles like this with the beam?
Because right now it only succeeds for static weight measurement. Because it's too complex to calibrate the weight in motion. So we have to try it. We have to.
I'm watching people. I think it will work anyway. When you have this weight, it will give you a number. I don't know how you did your programming, but my concept is that you won't get the full weight when your weight is distributed. The weight is distributed and you're measuring locally here. So then you will get only the weight of that. You don't get the weight of the back track. Second axle, which is out, you won't get it here. That's my thing. Now his point, like this, and then you get the other, and then that you have to check it also, right? When you get this and then you get this, how you're going to add, but you not add because also the weight here and the weight here, then you miss the weight in the middle. If it is, let's say, loaded truck with pickup. Anyway, you understand my point? So that's why I think on that one, this one, it might be slightly not proper. You might get maybe two beams, but then two beams again, it will be for specific tracks and size. So then the first axle will be there, this way, and here, and then you get the weight. Therefore, instead of having a whole weight that it is actually a sheet, and then the whole track is on it. Right? That's one thing about the measuring technique that I have. What else? I mean, for your design spec, you have. Can you go to design spec quickly, and then maybe some calculation? Okay, no. So here you have that one is the weight, right? Well, then this 90% whatever accuracy and stuff. So can you show me one? I mean, not the first one. The first one kind of probably straightforward. Can you show me some design analysis? I mean, maybe okay, the first one and one of the other, just to show you design analysis for the component, how you find it.
So the second.
Start with the first one, which is kind of the easy one. Let's say straight. Let me see how you did it. Because this one, the first one is what? Is like you get the beam or what?
Yeah, the first one is the key.
The beam, okay? So how did you get the dimension of the beam or
Uh,
the characteristic of the beam?
Actually, for this part, it is done by the other member.
And?
But he couldn't be with us today because of family member.
Okay, and so what do I do for this one?
Master this.
Okay, fine. Let's say I'm not convinced. Show me one that you did, let's say, or one of you did.
For the second one, the camera part. Okay, so for the camera part is our target for this part is the camera can detect the vehicle present and plate number within 5 meters before the bollard.
Okay, why 5 meter?
Why 5 meters? Because in the 5 meter range, it is the most suitable length for the camera to get the full view of the vehicle.
Yeah, because now you know the camera, you have the camera in your head. So if it is that one, then you should put maybe as an engineer target, that it should be within 5 meters or whatever it is. But now you know the camera that you have in your mind, that it would be better if it is 5. So already you designed in your head without design based on the design number. Okay. Because here the design number is, if I go back, is 80% or 90% detection, right?
Yes.
So how is that 80-90% detection?
80-90%.
Decided on your camera. How can I?
So from here is basically the 90% is basically on the software. The software can recognize the vehicle size, the rectangle size, and after the camera can detect the plate size, and then
No. See, now you're describing the solution. I don't want the solution. I understand how you. I want to see how did you get the camera, because here the camera is one of the components in your system. And it should have that 80% ability to detect the plate. I want to go from that 80% ability, and then I go and I find, okay, I need this camera that has this feature to achieve that 80%. That's my point. So how the calculation that is involved?
So the calculation that is involved is actually to determine the camera specification. So first, when we set the distance within 5 meters, we set the speed of the vehicle which will be around 90 km/h. So distance between the bollard and the vehicle with the speed is
Okay, still we don't get my point. I think. So what is the 80%, the engineering target that you put? 80% ability to detect the plate. Where it is involved in the calculation?
actually at here. The pixel for the camera.
Yeah, where 80% or 90% or 85%? What is it? To decide to choose the pixel or whatever, or the distance or whatever it is. That's my point. See, your things here, again, not related to your engineering target. You should start from that 85%. For that, I need the camera to be located 5 meters. Okay, then whatever. Then about that 5 meters, I do it. Then I need, the camera needs to have this much pixel. Then I go, I have this model that has that pixel or higher, then I pick that model. But it should start from that 85% because that's what you put as your engineering target. If it is not, you cannot use the 85% and the 5 meter will help you to find that, the engineering target should be 5 meters instead of 85%. You should be able to detect the plate from a distance of 5 meters. Then I use the 5 meter blah, blah, and then I get the pixel or whatever, the focus or whatever it is, which is characteristic of the camera. So then I can pick one of the camera that out of the 1,000 cameras that they are there in the market. Okay?
So means that the engineering target can be the length for the.
I'm not sure, but it should be something, of course, from your thing, but probably the plate is right also. Because you want to be able to detect the plate because you're going to give a compound to the guy, yeah? So you have to get the right plate. But Based on that detection, then I want to see how that affects basically the characteristic of the camera. How I'm going to decide between these three cameras, which one I'm going to use basically, right? So the same for all the other components. It should be like that. It should be engineer terms, not just calculation and number, which are not linked actually to engineer terms. Okay? Yeah, I think that's. Okay, I'm done.
Okay. Dr. Fas? Oh, your group. Okay, nothing from me. I just already asked just now. Okay, thank you.